Okay, my screen is visible, Harsh? Okay, let us start. Thank you. Okay, in our previous lecture, we talked about the theory behind the amplitude modulation. And in that lecture, we discussed how the modulation process takes place. And we represented a modulating signal with the help of this first diagram, which is varying with respect to time. This information signal or modulating signal is changing with respect to time, and the expression for this signal is sorry, ये दोनों ऊपर नीचे exchange हो गए हैं. The modulating signal is xt, which is cos omega ct, and the carrier wave is ct, as C represents, is equal to a cos omega ct. Here capital A is the amplitude of the carrier wave, which is constant. Frequency is high of the carrier wave. Why high? Because we know for longer transmission, larger distance transmission, we want to have much energetic signal so that even after attenuation, the is not lost. So what actually happens in the modulating process is that this modulating signal xt cos omega ct is superimposed upon this carrier signal ct a cos omega ct. Then in the modulation process, this modulating signal will try to change the characteristic properties of this carrier wave. And what are the characteristic properties of this carrier wave? These are the amplitude, the phase, the frequency, the width, etc. So in amplitude modulation, the amplitude of the carrier wave will be changed, and the shape of the envelope will now look like similar to the modulating signal. So mathematically, how to represent this? As we can see, before point P, there is no superimposition of the modulating signal. So carrier wave does not change its characteristic property, that is amplitude, frequency or phase. But at point P, we have superimposed the modulating signal. After the superimposition of the modulating signal at point P, there is a change in amplitude of the carrier wave. And this change in amplitude is proportional to the instantaneous change in the modulating signal. So obviously, this physical picture of the modulating process, amplitude modulating process, this third diagram, should be represented by a mathematical expression. And that mathematical expression should include both the carrier wave and the modulating wave, plus the effect of superimposition of modulating wave on the carrier wave. So this cos omega ct has the information of the modulating wave and carrier wave, and this amplitude a plus xt has the information of variation in amplitude in the modulating signal when it is superimposed upon a carrier wave. This a is the amplitude, constant amplitude of the carrier signal, whereas xt is the amplitude of the modulating signal. And you can clearly see in this diagram, if you can see the cursor on my screen, you can see the amplitude of the carrier modulating signal is continuously varying. It is time varying, and it is varying continuously. So A is constant for the carrier wave, and we have a time varying modulating signal amplitude. So after superimposition, the total amplitude of the modulated wave will be a plus xt. So xt will be continuously changing. This results into a new wave that is called as modulated wave, which has the information of both the modulating wave as well as the carrier. So this is all what we have studied in our previous lecture. Now let us start the next topic of our syllabus. The next topic of our syllabus is the spectrum of frequency domain representation. If you look at the previous expression for the carrier wave, for the modulating signal and modulated signal, every expression of wave has cos omega ct in the argument. So that is called as the time domain analysis of the signal, because here we will talk about the voltage and current variations in the space with respect to time. But at sometimes we require to study the amplitude, phase, frequency variation with respect to frequency. So in case of spectrum analysis, we have to shift our equations from time domain to frequency domain. So if you remember, here we will make use of a quantity that you have studied in your mathematics in the lower class. What basically spectrum is? Spectrum means the range of frequencies present in the allowed bandwidth. But our expression of the carrier wave, modulating wave and modulated waves, they all are in time domain. So we have to change time domain equations into frequency domain equations. So for this, what we will do, we will use a concept of mathematics studied in lower classes, which is called as Fourier Transform. In Fourier Transform, we transform a function in x to a function in y. So here we have a function in t, that is time domain analysis, and we want to convert this function into frequency domain analysis, that is transfer from t to omega. So now we will convert all equations into frequency domain. Here we have to also use an expression for the exponential iota theta is written as e raised to power iota theta. Cos iota theta, cos theta can be written in terms of the exponential function. Similarly, sin theta can also be written in terms of the exponential function. So here we will make use of these two quantities, that is frequency shifting theorem of Fourier transform and sine cosine functions in terms of exponential quantities. So let us start the spectrum of amplitude modulated wave in frequency domain and representation. So let us again start with the original modulating signal and the carrier wave. Carrier is a cos omega ct. The modulating signal is xt cos omega ct. The superimposed, that is modulated signal, is given by st, which is equal to a plus xt into cos omega ct. So these are the three equations which we have already derived or discussed, which are in time domain analysis. So our purpose is to convert these three equations into frequency domain by making use of a Fourier transform and some simple trigonometric formulas. So to do this, to do the Fourier transform, let us assume that small st, which is modulated signal, has a Fourier transform given by capital S omega. Similarly, the carrier wave, which is given by ct, has a Fourier transform of capital C omega. And in the same manner, let us say small xt, which is modulating signal, has Fourier transform is equal to capital X omega. So we can now easily say that small xt, small ct, small st are the modulating signal, carrier wave and modulated signal in time domain. We want to convert these into frequency domain given by capital X omega, capital C omega, capital S omega for the modulating signal, carrier wave and modulated signal. So for this, we consider that a band is limited in an interval which is given by plus and minus omega. Hold for a minute, I have to take a call in between. Lecture में हूँ sorry for the interruption. So let us take the bandwidth in between plus minus omega m, and now let us try to convert the time domain equations into frequency domain equations by making use of Fourier transform as well as the trigonometric expressions for sine cosine functions. Now let us say that the carrier wave has two impulses, that is plus and minus omega c. So let us say that the cos omega t is represented by small variation in frequency around these two impulses, omega c and minus omega c, and these small variations are given by omega plus omega c and omega minus omega c. Omega c plus omega c and minus omega c are the two impulses present in the cosine function. Since the carrier signal has equation a cos omega ct, so equation 3.7 is for cosine function, and we want to write the expression for the carrier wave. So we multiply the cosine function with respect to a, that is equation 7 has to be multiplied, 3.7 has to be multiplied by capital A on the both hand side, left as well as right hand side, and we get capital A cos omega ct is equal to pi a, small variation in the frequency around the plus omega c and minus omega c, which are the two impulses present in the cosine function. Now amplitude modulated wave we already know is also given by xt plus a into cos omega ct, or xt cos omega ct plus a cos omega ct. This is modulated wave, amplitude modulated wave. Now we want to transfer the equation from time domain analysis, that is equation 3.10. I am talking about the last equation on this page, 3.10. Here this xt is a function which has to be converted into capital X omega, which is in omega. So to do this, we make use of a frequency shifting theorem. If you can see here, let me use the color for this. The frequency shifting theorem you must have studied in your Fourier transform in the mathematics. So we are going to use it directly, so you have to remember it directly, the frequency shifting theorem. So according to frequency shifting theorem, if we multiply a function by exponential function j omega ct, then this time domain function will change into a frequency domain function. And shifting means here this omega is frequency and it has shifted by omega c, which is the impulse in the cosine function already mentioned. That's why the name is frequency shifting theorem, because it has shifted the frequency by plus omega c or minus omega c. So this frequency shifting theorem property states that if a signal is xt has to be multiplied by some exponential function in time domain, then its spectrum is in x omega, and in frequency domain its frequency will be shifted by an amount omega ct, and this omega ct is nothing but the frequency present in factor, exponential factor. So what if here we multiply with e raised to power exponential 2j omega ct, so in that case the frequency shift would have been 2 omega c. Let us say we have written exponential j n omega ct. In that case the frequency will be shifted n omega c times. So this is the property of frequency shifting theorem, that whenever we multiply a function which is in time domain by exponential function, then it will change or shift its frequency by the factor present in the exponential function, and the factor which is present here in the exponential function is omega c. So correspondingly, the shift in the frequency will be omega c. So similarly, if you multiply the function with exponential minus j omega ct, then there will be shift in the function by omega c, but now it will be added. If you see the previous equation, in previous equation we have multiplied by exponential j omega ct, that is plus function, then the frequency has shifted in lower frequency region by subtracting omega c minus omega c from omega. But if we multiply, if we take the exponential minus j omega ct, then again will be shift omega c, but it will be shifted to higher frequencies now, and we will get a shifted function as x omega plus omega c. So let us now talk about the modulating signal, which is xt cos omega ct. Here we have used a property of cosine function which can be written in terms of the exponential terms. So cosine function in cos theta in terms of exponential function we know is e raised to power eta theta plus e raised to power minus eta theta by 2. And cosine function, sine function we know is given by e raised to power eta theta minus e raised to power minus eta theta divided by 2 eta. So here we have used the frequency shifting theorem from Fourier analysis and the trigonometric expression for cosine function, which is equal to e raised to power eta theta plus e raised to power minus eta theta by 2. Here theta is omega ct, that's why it is equal to xt, e raised to power j omega ct plus e raised to power minus j omega ct divided by 2. Now let us multiply this xt with the bracketed terms. If we multiply with the both terms, we will get half xt e raised to power j omega ct plus half xt e raised to power minus j omega ct. And here now we know that this e raised to power j omega ct and e raised to power minus j omega ct by frequency shifting theorem are equal to x omega minus omega c plus s x omega plus omega c. Where this equation 3.14 came from? Equation 3.14 came from the 3.10, according to which if xt is multiplied by e raised to power j omega ct, then by frequency shifting theorem according to Fourier analysis, the frequency will be shifted to lower frequency and new frequency will be omega minus omega c. Similarly, if we multiply if we take the exponential function as minus j omega ct, then according to frequency shifting theorem, according to Fourier analysis, the frequency will be shifted. In this case, the frequency shift will be in the higher frequency region, and new frequency will be omega plus omega c. So in place of this e raised to power j omega ct, e raised to power minus j omega ct in equation 3.13, now we can substitute. We are talking about this expression and this expression. In equation 3.13, for xt e raised to power j omega ct, we know it is equal to capital X omega minus omega c, and xt into e raised to power minus j omega ct is equal to x, the function of omega plus omega c. So now in equation 3.14, what we have achieved, we have converted the time domain equation into a frequency domain equation. So we have achieved this for the first expression. Now the second expression is the carrier wave, and carrier wave expression is equal to a cosine omega ct. So now again this has to be converted in the same pattern as equation 3.14 is obtained, which is for modulating signal, and this is for equation 3.15 for the carrier signal. So carrier signal equation is also shifted into frequency domain, and it is equal to pi a delta omega plus omega c plus delta omega minus omega c, this omega plus omega c and omega minus omega c are the change in frequency or shift in the frequency of carrier wave around the impulses present in the carrier wave. Now, how actually the whole process will look like? This is our modulating signal. Let us call it as small m, modulating signal. This is our carrier wave, and this is amplitude modulated wave. So this is in time. All these three signals earlier were present in time domain. You can see them. The x-axis of every signal is in the time domain, and now we have achieved them in the frequency domain. Here the modulating signal has the bandwidth which lies between plus minus omega m. Carrier frequency has the two impulses omega c and minus omega c. The variation in carrier will now be around this plus minus omega c. And when this modulating signal is superimposed upon the carrier, then this will try to change the amplitude of the carrier wave or envelope of the carrier wave, and the shape of envelope of the carrier wave is somewhat similar to the modulating signal, but it is in time domain. In case of frequency domain, we can say that after superimposition or after amplitude modulation, we will get two types of frequencies. That is frequency which will spread around the minus omega c, and frequencies which will lie between twice omega m, which is the bandwidth of the modulating signal. So finally, we will have an expression of modulated signal or amplitude modulated expression. We have discussed about the modulating expression, which is in time domain, which is converted into frequency domain. We have talked about the carrier wave expression, which is in time domain, which is converted into frequency domain. So after the superimposition of modulating wave on the carrier signal, we will get amplitude modulated signal, that is modulated wave, which is equal to 3.16 equation, and it has two parts. Each part represents a specific term which we will discuss now. So equation 3.16 can be divided into two parts. This is called as first part, and this equation is called as the second part. So the spectrum of original or baseband signal is shifted by plus minus omega c. This first part represents the spectrum of original or baseband signal, and this second part represents the carrier wave. This represents the carrier wave, and this represents the modulating signal. So equation 3.16 has three separate parts. Left hand side represents the amplitude modulated wave, which is obtained by converting the modulating signal, which is in time domain, the carrier signal or carrier wave, which is in time domain. They are converted into frequency domain. After frequency domain conversion, the expression for amplitude modulated wave is given by equation 3.16. It has two parts. First part represents the modulating signal, which shifts around the impulses omega c, and a carrier wave or carrier frequency which also shifts around the modulating, which also shifts around the impulses present in the carrier wave. Now this is the last slide for today's lecture. So we can draw the important conclusions from the amplitude modulated wave, and these important conclusions are: for positive frequencies, a portion of the amplitude modulated wave is lying above the carrier frequency, that is omega plus omega c. This type of band present in the frequency spectrum is called as upper band, whereas there is a symmetrical portion below the carrier frequency also, which is equal to omega minus omega c. This is called as lower sideband. But this is for the positive frequency. If we talk about the negative frequency, then the upper sideband is represented by omega minus omega c, and lower sideband will be represented by omega plus omega c, which is just the reverse of positive frequency, upper sideband and the lower sidebands. Second point, we generally keep the carrier frequency higher than the modulating frequency, which means that we want to ensure the two sidebands does not overlap, and a long distance transmission is also possible. Now the third point, at this point it may be noted that the negative frequencies appeared in the spectrum analysis is due to the exponential representation of Fourier transform. However, in actual practice we do not encounter the negative frequencies. It is just for the mathematical convenience and representation of Fourier transform. That's why we have to simultaneously consider the positive and negative frequencies. However, in real physical meaning, the real function of negative frequencies does not have any application. They do not find any meaning, means we do not have the negative frequencies. This is just simply a mathematical representation by applying the Fourier transform. In bandwidth, we always talk about the positive side only of the spectrum. Next point, the bandwidth is obtained by having highest frequency component present in the spectrum, and the highest frequency component present in the spectrum is given by omega c plus omega m, lowest component omega c minus omega m. So bandwidth, we know that we subtract fm, that is maximum component, fl, that is lower component, fm minus fl will be the bandwidth. So here the higher frequency component is omega c plus omega m, lower frequency component is omega c minus omega m. So to obtain the bandwidth, we have to subtract the lower frequency content from the higher frequency, and we obtain the bandwidth for the amplitude modulated wave as twice omega m. So bandwidth of the amplitude modulated wave is twice the highest frequency present in the baseband or modulating signal.